I will speak on rationality of quotients of abelian varieties and computer algebra. Professor Chung?
Yeah. So first of all, I like to thank the organizer for the invitation. So let me, I'm opening my iPad to share the screen. Okay. Yeah. Mm. Okay. This is not. Okay. Yes. Yeah. So my talk is about some ideas about how we can try to show that a quotient of an abelian variety is.
Read a little bit more.
What do you say?
Read a little bit louder.
Okay. Yeah. So I will try to say louder. So the idea is that I think probably we need to use some computer algebra is kind of a way for us to try to solve polynomial equations fast and efficiently, and I think that might be a good method to for this question. And so here the plan, and I will say mostly will be about the reviews of results that already known, and then so here some references related to this question. Of course, there are also other references on dynamical systems, which I will mention later. So first is the motivation for this question. So there are two questions, two motivations. So one is the geometric motivation, try to understand about the relations between several different notions in geometry. So first is rational variety. So this is variety X, not is bidirectional to the R5 space. And then second one is unirational, something that has dominant rational map from the R5 space. And third one is rationally connected. Is roughly speaking, that means that if we give 2 points x, y, we can connect them by a chain of rational curves. So the geometric motivations that what I said was the difference between these two types. So in particular, if we have x quotient of an abelian variety, so should they be the same? And then that is geometric motivation. And the second is the dynamical motivation. So that is we want to construct interesting varieties which have interesting automation groups. So of course there are many notions of interesting automation groups. So for example, you can see recently there are many work on that, but in my talk, what I mean to be an interesting map is this kind of thing that it's not coming from a smaller dimension no map. So this the notion is a primitive map, which is defined by Zhang. Let's have building block for rational map. So it's a map S from X to X is primitive if it doesn't come from smaller mass from y to y, and this is not non-trivial. That means that the dimension of y should be bigger than equal 1, but should be less than the dimension of x, dimension of x. And one other thing of interesting automation which comes from smooth dynamical systems that F, a map F has positive topological entropy. So this topological notion, but then later I will mention a way to compute it from geometric quantities. So then interesting interesting variety. Of course, we want a rational or unirational or rationally connected variety, and then this is kind of an open question in complex dynamics. That is, can we find like rational variety or unirational or rationally connected variety X, which has primitive automatism and it has positive entropy. So of course, even in dimension 2, okay, even in dimension 2, the answer is not that trivial. So only in around maybe 15 years ago that some large family on blocks of T2 were constructed by Bedford Kim and Mark Bullen. And in dimension 3, it was not the big people was didn't know about, and then I at least so I think that if you blow up T3 maybe by points or curves, and you can do a finite number of blow up, and then I think that you cannot find any primitive automaton about the interface. Even if you don't care about the primitivity condition, then you don't. I don't think that you have you can find any such thing. And then this was supported by result by the Lesutre. So he proved that high up, if we blow up P3 a finite number of times, then we cannot find any automation F x to x, so that with positive entropy and high up is primitive, so kind of similar to that. Actually, his result is a little bit weak, a little bit. It used terms of dynamical decrease, but somehow it supports his that I mean opinion. So here's okay. So here's the definition of entropy in terms of geometric quantities. So if we have a map F from X to X, holomorphic map, then we can define simple quantities called dynamical degree, the type dynamical degree, which is simulated the vector radius of the linear map from A to Jx to itself. And then there's a very famous result by Gomov and Jomdin, who said that the topological entropy is the log of the maximum of all the lambda j. So if you want to get a positive entropy, you just need to find a map F so that the one of the lambda j is bigger than 1. And then the relations of lambda j's that they kind of relate quite nicely under a fibration. So if you have a fibration from X to Y, and then this is also true. It's not just for F holomorphic, but also for rational mass, and even you can also still say something in view of in the if f and g are corresponding, that is so here's a special case that if pi is finite to one map, then the dynamical degrees of f and of g are the same. So, for example, if you want to construct, so a way to go is that okay, yeah. So here's some remarks that we can also define this in positive characteristic, and then the known result in complex case. If you extend those to positive characteristics, then you will have kind of a generalization of Weier's Riemann hypothesis, which was proved by Delin. Still, I cannot prove that conjecture, but we have some evidence. So now is the first thing. So I mean the lambda j f equal lambda j g, which I wrote before, is known for in complex case. But if you can prove it for positive characteristics, then you have a generalization of Weiss Riemann hypothesis. And what I can prove is that if f and g, f is an endomorphism, then kind of effect maximum, then you get some consequence of that thing. And then in the case of abelian varieties, then the conjecture is now known by resolved by Fihu. He proved that that's the case for endomorphism of abelian varieties. So anyway, so this just a remark in positive characteristics. Now, so let's see how we can try to construct a primitive algorithm a positive entropy in dimension 3 on rational varieties. And as I said, if you try to blow up x, then B3, then you have no hope. And so one way to use that the relation between of diameter degrees under finite finite to one map. So what we can do is that if we have x, if x has a good map, a primitive automation positive entropy, and then we have a finite group G acting on x, and assume that it is f is invariant under this action, and then you consider the quotient, and then on the quotient we also have a primitive automation positive entropy. And what we need to do is just try to find an x so that the quotient is has the property we want. For example, we want it to be rational or unirational or rationally connected. So that's one idea to go. And here's the proof, which basically just what I just said. Yes, and this is the approach that I said. And the thing is that on abelian varieties, we have a lot of interesting math. So one way to go is that we try to find a quotient of abelian varieties, which have the desired geometric properties. So now I come to think about some generalities in on finite quotients of abelian varieties. So we take S an abelian variety and see the finite group acting on X. And here we can define a quantity called H of an automation, which is just if the eigenvalues of T, of course, they are all of the form e to 2 pi I x, where x a rational number, and then between 0 and 1, and we define H T to be the sum of those numbers on all eigenvalues. And this is the right type condition. Except that we want that the h of h equals to 1 if h not identity. And here's another related notion, unit rule, which just means that we have a dominant map from y corresponding 1 to x, where which does not come from y. And here is the table resolved by Lassen, which says that XOT is unit rule is equivalent to XOT is rationally connected. So by the way, for unit rule in general is quicker than rationally connected, but on for quotient of even for of Calabi-Young, then they're the same, and they're the same as the group G does not satisfy the right type condition. And now, so here, so yeah, so this the question I asked from beginning. So if X is a Abelian variety and we have finite quotient, and if X over T is say rationally connected, so would it also be unirational or rational? Or yeah. And here's another theorem by also Lassen. And if X is a simple Abelian variety, then bigger than 4, and X and T acting on X, and X of T has canonical singularities, and Taylor dimension is 0. And here another result by Obiso that if X of T has a singular point worse than canonical, so it's kind of in opposite situation than the theorem by Lassen. Then X of T is universal, and this proof uses complex dynamics, so it's yeah, quite interesting. Okay, so now from now on, I will assume that X is I will look at the quotient of product of the same Abelian variety, and so so most of the top will be all of the top here maybe will be when A is an elliptic curve, but hopefully maybe we can also do something with A not an elliptic curve. And the question is, and why do we want this testing? We want this testing only because we want to have interest in automation. Because if we have a product of Abelian variety, then it's easy to cook up interesting automation by looking at a say matrices with coefficient in P acting on coordinates on the coordinates. Of course, if we only consider about rationality or irrationality, then maybe we can look at, like, for example, A1 plus A2 plus AN and so on. Now, so we here's the if E is an elliptic curve, then of course we know about what is the automation group of E. It's actually related to the J invariant. So either automation is just the has order 2 or order 4 or order 6, and the one with order 4 is there's only one, it's one, and then the one order 6 also only one. And we will want to look at E and OT, and T as diagonally on E, and from some calculations with the singularities, we see that if we want EMOT to have non-canonical singularities, then M must be less than order of T. So for example, for this E4, then we can only take M equals 2 or 3, of course also 1, and then for E6 we can only take 2, 3, 4, 5. And the case M equals 1 or 2 is trivial, so from now on we will look at M equals 3 and up. So by Augusto theorem, all the interesting cases, they are all unique. So that means that E4 to 3 over the group E4 is unique, and also E3, E6 over 3 over T6, or E6 4 over T6, E6 5 over T6, they are unique. So by the way, so interesting cases, we have not too many, only these 4 varieties. And so then from this we see right away that if we want to show that they are rational or unirational, then we need to do a lot of calculations, because if we can use some very general results here, then that seems not right, because we have not too many of them. So here example 1, this is the first explicit example of a rational threefold having positive entropy, primitive automation positive entropy. That is Z equal E6 3 over T6, and the claim is that it is rational. And the thing is that to show that we need to do very ad hoc calculations, so there is no kind of systematic way to do it from, I mean, for the known results now. So what happened is that we can start from the equation for E6. This is y, the R5 part, which is y2 equal x3 minus 1, and then we calculate the invariant part, which is C yi yj and C x1i x2j x3k, where I plus j plus k equals 3. And then we do some a tensor variables, some very special tensor variables, and then we see that we reduce it to C y1 square, y2 over y1, y3 over y1, x2 over x1, x3 over x1, and then at the end we can get this equation. So G is birational to conic bundle W3 minus 1, C2 minus 1 equals G3 minus 1, X2 minus 1. And so of course this conic bundle, if you protect it to WT coordinate, and it has a rational section F equals 1, 1. So it's rational. And here is an explanation of why A36 have a primitive automation of positive entropy. So you just take A, some 3 by 3 matrix, which is invertible, and with eigenvalues zeta 1, zeta 2, zeta 3, where zeta 1 absolutely is bigger than 1, and then bigger than zeta 2, zeta 3. So if you compare the spectral radius of A, then you find that lambda 1A to the zeta 1 square, which is bigger than 1. And then zeta 2, lambda 2a, zeta 1 square, zeta 2 square would be less than zeta 1 square. And then there's a lemma using again the relation between diameter decrease and uh, the quotient. So that's if we have mass f and lambda 1 bigger than lambda 2, then it's a primitive. So it's quite an easy to check criterion if you want to construct primitive mass. So there are many maps that don't satisfy this, but still people can manage to show that it's primitive. But anyway, this is an easy way to do. And then example 2, this is interesting because it has a long history. It comes from the book, it's being mentioned in the book by Juno. And then Kamana showed that it is rationally connected. And he also showed that the two-dimensional analog is actually the minimal resolution of it is a composition of smooth flow of P2. And then the question is, can we have like E3 4 over T4 in the minimal resolution? Can it be a flow up of P3, for example? And as I mentioned before about the theorem by Les-Dutré, we know that it cannot. And then later, I will mention also another result by other people which also show that thing. And then so Catanese, Augusto, and I, we show that the universal. So this is the universal, yeah. And the thing is, we also need to do like ad hoc calculation like before. And we get this v bidirectional to this. Again, now we have a conic bundle, but we have no section, so we don't know if it's rational or not. On the other hand, if after we consider 41 map change like b equal x square, beta equal t square, then of course we have section a equals x and b beta and a equals x and alpha equals t. So that is a rational. So it means that we have a dominant map from a rational threefold to this one. So this one is unirational. And now after knowing about this, then Kolyotkin and Selena, he can use this result about he has a criterion for where the conic bundle is rational, irrational or not, and then he could use and this uses pro or true, and he could show that okay, this one is rational. But his proof is of course he uses, so it's very indirect, and so the question is can we have a more direct proof? And then here's another result which shows that this minimal resolution cannot be a composition of flow of the P3 by BC, Cassini, and Tyson. And the idea is to look at this map on the community. So if we have A2, then we look at alpha to alpha 3. And then we look at what happens to the Hessian of this map under blow up. So if you blow a point, so what happens to the rank, and then if you blow up a curve, what happens to the rank, and somehow they can show that you cannot go from P3. And then this is the other one, the third one in our four spectral varieties. This one then by Catalyst and Obiso, where they saw that it's a universal. And again, they also still use quite ad hoc calculations, and they show that S birational to this one with the cubic cubic hypersurface in the field over P1, P2, and here the coefficient are quite special, so degree 3 or 2, and then they use some special classical results to show that this one is actually universal, and even they can prove that there is a map of degree less than equal 6 over this field, dominant map. But they also show that S is not K-rational. So now we don't know if this one is rational or not. We know that it's universal. And here's a summary of what we know. So the for spectral varieties, so for the E43 over T4, then it's rational, and but anyway, but the proof is quite indirect. And then E63 over T6 is rational. This the proof is ad hoc, but it's quite easy. And then E64 over T4 is universal, but we don't know if it's rational or not. And E65 over T6, we know it's rationally connected because of result by Obiso, but we don't know anything else. Anyway, so that's what we know. Now, as I said, maybe if we have some ways to use computer, maybe it can help. And here is the way to this a way by in a paper by Anton Melich, and his idea is that he tried to construct it's basically a family of rational curves on this X, and then his main the main tool is this lemma 2.1 is his paper. So his paper is an archive, but since he put it there, I didn't see any updates, so I don't know if he have any progress on this. But this is the main tool. So if we have a family of rational curves on variety X, and if we have a hypersurface, and assume that we have an open subset. Now we assume that for a transit point in X, then there's exactly only one curve which goes from X, goes to this point, and the same for a transit point on Z. And assume also that the curves are not contained in Z, in this hypersurface. Now is the conclusion. If Z is universal, then X also universal. And if we want to show that X is rational, we need more. So we need that Z rational, of course. But then we also need one condition that the number of intersection points between a curve and this open set in this hypersurface is one. Yeah. So that's and then here's what he the way he constructs the rational curve. So he writes the elliptic curve in the weighted projective space XA by this equation XA minus YB equals GC. And then he choose one, he fix one polynomial R, so that's it fixed. And then no, it's not fixed, but if we fix an R, and then for any I from 1 to n, so here we want to look on the e to the n over a finite group, and he looks for polynomial pi and qi. That's satisfy the same equation pia minus qib equal r2. And if we have that, then we have a map E theta from this curve RUV equal WC into the elliptic curve. And if we do this for every coordinate, then we get a map from C theta into the product. And then if we take quotient, we get the quotient of C theta will be a rational curve. So we have a rational curve. And then if we vary the polynomials pi, qi, and r, then we get a family of rational curve in this x. And then by some calculation on the dimension. So if we want to have only a finite number of such curves going through a point, and assume the degree of P is Kc over A, and degree of Q is Kc over B, and degree of R is Kc, and K must be equal to over C minus N. So that's a number, and then we get that relation. And then he needs more calculations. Anyway, so what is so okay? So let's look at his lemma 2.1 again. So what he will choose for Z will be this hypersurface. That is the hypersurface dV where v1 x1 plus dot 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 plus vn x1 equals 0. So that's what he choose for Z. And then he reduces everything to some matrices which we need to compute, and then also there's some other matrices H we need to compare, and then there also M. So here's one example where and the idea is that if we can use V, so that so we know that the number of intersection between a curve and this hypersurface is AC theta times V times V star. So if this number is and if we take out some points, some vector points in some like up infinity, and we only look at alpha coordinate, and if that number is like smaller than, if that number is smaller than 2 times order 3, then after we take quotient, then the intersection is only 1, and that's we have lemma 2.1. So what happens is that he did several calculations. For example, in the case of E to 2 and ABC 3. So in this case, the group is we have the elliptic curve automation curve has order 3, and now gamma order 3, and then he computed two possibilities like this, and then he got he could find that this number is he could find some V, so that the norm is 5, and we see that 5 over 3 is less than 2. So this one is a good one, and lemma 2.1 is 5. So this is this shows that E2 over gamma is rational. Of course, this is well, but this is a quite systematic way to see it, and also you can see you get quality of rational curve. And then there are some very mysterious claims in his paper that is in his example 3. I'm not sure if what he claimed here. I'm not sure if he claims that he showed that this lemma 2.4 is satisfied for E34 over T4. So we know that for this statement, for this thing, we know that it's rational by Colliot-Thielen, but Colliot-Thielen's proof is very indirect. And now when you look at example 5 in Anton paper, it's very unclear what he claims here. And then on example 6, Now this interesting because this is the corresponding to the case of E6 to 4 over T6, which we don't know if it's rational or not. And he said that he looks on a field which is very big, 100,003, and then he found that lemma 211 is a size for that prime number over that field. So anyway, so I think that maybe this is number 6. Maybe it's interesting if people who can work out this system polynomial equation. Anyway, so here's what I think about his approach. That I think that his condition 1 versus 2 versus 3 versus 8 probably seems easy to be satisfied. So it seems that it means that for to show that such a quotient is unirational, maybe this approach is quite a good one and a systematic one. But for 1 plus 2 plus 3 plus b, which wants to show that rational, it may be more difficult. And this one I wrote that probably there is a more systematic way and not ad hoc way to prove that XL gamma is unirational for X and the Abelian variety and gamma finite group. And on my ongoing work with my Augusto, and what we are doing is we are constructing another family of curves, not those curves. We don't know if maybe at the end they may be the same, but maybe not. Which are easier to compute, and yeah. So at least we can we are trying to show that the condition 1 plus 2 plus 3 plus 8 in lemma 2.1 of unformally is satisfied. And that's yes, my talk. Thank you.
Thank you.
Okay, thank you.
Yeah.
Are there any questions from the audience?
For the algebraic geometry, is there topological entropy or the automation is interesting?
You mean this one? Topological entropy?
Yes, as rather in the beginning, you mentioned that there referring to the complex dynamical system, about the discussion of the topological entropy.
Yeah, right.
Yeah, but for the other geometry is that the topological entropy notion or the topological entropy have some meaning on in their central so argument of the algebraic geometry in row dimension, just so related to the automation groups.
So I understand that you want to know whether the topological entropy has some interesting consequences for automation group. Is that your question? Yeah, so I think, for example, there results first by Dean and Sydney, and later I think it was extended by many people that if you have yeah, I don't remember correctly, but it says something like if you have a group acting on compact Taylor manifold and all of the elements except the identity has positive entropy, then you have some constraints on the group. I think it's I don't remember correctly, but it's something like that. And then later it was I think recently I don't follow, but I think now it's very much generalized. Specify that six alternatives, something like that. I don't remember. And then also I mentioned that and it's interesting in positive characteristics can we define notion of
여보세요?
that it's still open in positive characteristics. And this the thing is we in positive characteristics we don't know what is a good topology to use.
머리 한 사람 또 팔겠지.
Yeah.
사겠다는 사람들이 잔뜩 줄 서 있을 거야. 아니 그래 내용 모르는 사람들은 또 여전히 또 사겠다고 줄 서 있는 사람들 많을 거라고.
For example, people try to use the periodic topology, but then chat path and one person I don't remember his name for now, but they show that if you use periodic topology, then even on for map in dimension 1, you don't have the expected
저기 정혜원 그다음에
you don't have this here now.
두 명씩 데리고 할 수 있다고.
Yeah, and so it seems to me that that means that periodic topology is not the right one
두 사람을 더 데리고 오면 팀 코스트는 비싸진데.
In a field that is not complex.
아니 알았어. 자네랑 나랑 안 칠 경우를 얘기하는 거야 난 지금. 그런 경우는 엑스트라로 비용이 많이 얼마나 들어가는데 그러면?
I mean the difficult thing is to try to define a topological entropy so that we have this Gromov-Yondin formula that for now until now even in dimension 1 no one knows, and I think it's a good topology also related to this whether we can solve this conjecture. As I said, it's a generalization of Wise Riemann hypothesis. So they said that, so maybe I said a little bit about it, I could decrease how it's related to Wise Riemann hypothesis. And that, so here we compute dynamical decrease in terms of pullback on commodity. But you can also compute a similar quantity on the tau group, and then the conjecture that I mentioned here is that these two numbers are the same, and if you can show that, then and you apply it for the Frobenius map, then you get a near proof of Weyer's Riemann hypothesis. So that's why it's more general. Yeah. So hopefully that maybe answer your question.
Okay. Any other questions?
Okay. Any more questions? Okay. Then let's thank Professor Truong again. And
yeah. So
okay. So
everyone.
yeah.
Thank you.
Yeah. Hope you all stay healthy and safe.
Thank you.
And then see you again maybe next AGEA seminar.
Yeah, so see you again in 2 weeks. But please
2 weeks.
notice that our next AGEA seminar will be on Friday morning instead of afternoon. So that will be September 11th. Yeah, September 11th, in the morning of September 11th. Okay.
Thank you. See you.
Okay, see you.
Thank
See you.
you. See you. Bye.